video is covering is the concept of inverse. So we know, you guys already know what an inverse operation is. For example, if I said, what's the inverse of adding 2? It means how would you undo 2? So in other words, if I had x plus 2 equals 5, in order to solve that, what we normally do is subtract 2 from both sides, because that would give you x equals 3, right? But what you're really doing is doing the inverse operation, because I'm adding 2 to the x here. I want to do the inverse operation, which basically eliminates the operation that was just done. It undoes it. So I was adding 2 to x, and so then I subtracted 2, which undid what I had just added. Likewise, if I had 3x equals 9, we would solve that equation by doing the inverse operation. 3 times x is the operation, so the inverse operation would be divide by 3 on both sides. So we get x equals 3. So that's the idea of inverse operation. But we want today talk about inverse functions. So if you have a function that's, for example, f of x equals, say, 3x plus 7 divided by 4, let's say. So there's quite a few things. There's 3 different things happening to the x, right? The first thing you're doing to the x is multiplying by 3. The second thing you're doing would be adding 7, and then the third operation would be divide by 4. So if we wanted to produce a inverse function, which the notation looks like this, that means the inverse function of f. So basically what it does is it undoes whatever f does. So f would, again, it multiplies by 3 first, then it adds 7, and then finally it divides by 4. So the inverse function would have to undo all those things. And of course, just like when you get dressed, you put your undergarments on first, and then your shirt and pants, and then your coat. But when you undress, you have to take your coat off first, and then your shirt on down. So when we do things in a function, to undo them, we have to undo them in the reverse order that we did them. So here we multiplied by 3 first, added 7 second, and divided by 4 third. So when I'm doing the inverse operation, I go in the opposite direction, doing the inverse. When I build the inverse function, I go in the opposite direction and I do the inverse operation. So what's the inverse operation? Divide by 4, multiply by 4. So I multiply x by 4. Then what's the inverse operation of adding 7? That would be subtracting 7. So I put a minus 7 out here. And then what's the inverse operation of multiplying by 3? Dividing by 3. So now I can't just put a divide by 3 here at the end, because that would not make it be the last thing. So what I do is I put a whole big line there and put a 3 like that. So again, to check this, what you should have happening is you want to multiply by 4 first, subtract 7 next, and then divide by 3 last. And so if you look at this, did that happen? So x, first thing I do to x is multiply 4, check. The next thing I would do is subtract 7, check. And the very last thing I do would be divide by 3, check. So that means this is the inverse operation of that. Inverse function of that. Sorry, I keep saying that. Okay. So another important thing to understand about inverses is that their domain and range switch, meaning that the domain of this function would be the range of that function, and the range of the original function would be the domain of the inverse function. That's always true. And so another way to find inverse functions, if I have, like, for example, y equals 3x plus 7, it's the same thing I just had, right? Because the domain, we know the domain and range switch from one function to the other, what we can do is just switch the x and y, because you know the x is a list of all possible, or the domain is a list of all possible x values, and the range is a list of all possible y values. So if I wanted to create an inverse function for this, I would just write it as x equals 3y plus 7 divided by 4. And then I could just, if I wanted it in y equals form, I could just solve this equation for y. So I'd multiply both sides by 4, and notice I end up doing the same thing I did up above. So I multiply by 4 first, then I want to undo the 7. So I subtract 7 next, so I get 4x minus 7 is equal to 3y. And then finally at the end I'd have to get rid of that 3, so I divide both sides by 3. I get 4x minus 7 divided by 3 equals y. And notice it produces that same answer as we had up there. 4x minus 7 divided by 3, 4x minus 7 divided by 3. So you can make a list of what's being done in the original function and then undo it in the reverse order, or you can just switch the x and y and use your algebra skills to solve for y. Both of them will produce a inverse function. Okay, but again, keep in mind this is a really important thing as we go forward, that the domain and range are just switched. So a direct application of that is if we have a function that, for example, looks like this. There's a cute little function. So if we're wondering what the inverse function of this thing looks like, is think about the domain and range switching. So that means whatever is happening on the x-axis is now happening on the y-axis, and whatever was happening on the y-axis is now happening on the x-axis. So in this case, you know, we notice the y-intercept is x. I'm sorry, the y-intercept is 1. So in the inverse function, and this, by the way, is not that same function, it's a new function. So we'll call it g of x. So if I want to graph g prime of x, the inverse of g, since g is crossing the y-axis at 1, that means the inverse would be crossing the x-axis at 1. And since it looks like g has a horizontal asymptote, that would, on the x-axis, that would mean that the inverse function would have a vertical asymptote on the y-axis. So it looks something like that. And then finally, since g shoots off into space on this side, and it's heading up more in the y direction, but still a little bit in the x direction, the same thing would be happening over here, only it would be predominantly in the x direction, a little bit in the y direction. So this would be the inverse function of that. So notice what you discover if you look at that. That is just a reflection across the line y equals x. See that? We're not used to reflecting across diagonal lines, but if you were to reflect this function across that line, you'd end up on this function. And that's true of all inverse functions. An inverse function is a reflection across the line y equals x of its original function. Okay? Also using this domain and range flip idea. So if I was to take a original function and put inside of it its inverse, remember composite functions. So remember, this is undoing whatever that does and vice versa. So if we were to do that, this should undo everything that did and vice versa. So it should leave with just x. So this is a good way to test whether two functions are inverse of each other or not. You composite one inside the other, and if the answer is x, they're inverse functions of each other. If the answer is anything besides x, then they're not inverse functions. So if we take those two we did, let's say we had f of x is equal to, what was it, 3x plus 7. 3x plus 7 divided by 4. And we had this other one, g of x equals 4x minus 7 divided by 3. So let's say we're wondering if those two functions are inverse to each other. We actually already know they are because we created them, but let's say we didn't know that, kind of starting from scratch here. So one way to test that would be to go f of g of x, the composite thing that we worked on before. And the way that works is you go 3, just as a reminder, plus 7 over 4, right? So I write the outside function with the space where the x was, and I plug the g in there. So that would be 4x minus 7 over 3. And then we simplify it and see if we get an x. So notice the 3's cancel out, leaves me with 4x minus 7 plus 7 over 4. And of course, minus 7 plus 7 is 0, so that leaves me with 4x over 4. And 4 divided by 4 is 1, so that leaves me with an x. So sure enough, it passed the test. I did the composite of f and g and got x. If I did it the other way around, the same thing would happen. If I did g composite of f. And you can run that through if you don't believe me. You can test that out. So let's do one more example. Let's say that I have g of x is equal to 3x squared plus 5, and h of x is equal to the square root of x minus 5 divided by 3. So if you look at these two just on the onset, all the inverse operations are found in here, because this is multiplying by 3, that's dividing by 3, this is squaring, that's square rooting, this is adding 5, that's subtracting 5. But the question is, did we do them in the right order? So we're going to check to see if these are inverses of each other. So I'm going to go g of h of x, and so that would be 3 times something squared plus 5. And in here we'd put the square root of x minus 5 over 3. Okay, so now hopefully you see right away we're running into trouble, because if I square this, I get the 3, of course, stays alone. I get an x minus 5 on top and a 9 on the bottom, and a plus 5 is, of course, still sitting there. Okay, because when I square the square root of x minus 5, I get x minus 5. When I square 3, I get 9. So if we go to simplify this, we end up with x minus 5 over 3 plus 5. And notice that's not going to be equal to x. That would be x over 3 minus 5/3 plus 5, and sure enough, it's not equal to x. So we conclude that these are not inverses of each other. So let's just take one of them, like that guy, and find the inverse. Okay, then what is the inverse of h? Well, we can make a list. What's the first thing done to x? Looks like we're subtracting 5. The next thing is square root, and the last thing is divide by 3. So we're going to start by multiplying by 3, because that's the inverse operation of that. Then we're going to square, but make sure you square like this, because I want to square everything I've already done, because I want the multiplying by 3 to be first and the squaring to be second. So it should happen outside of the multiplying by 3. And then lastly, we have to undo subtracting 5, which means we would add 5. So that would be the inverse of h. So notice it's close. The difference here is the 3x is inside the square. Here the 3 is inside the square. Here the 3 is outside the square. And that's why this wasn't an inverse. Okay, so there's a quick little teaching video on finding inverse and testing inverse. Also a little bit about the graph of inverse, and again, that key concept that in an original function and its inverse, the domain and range are switched. Okay. Oh yeah, one other thing I wanted to talk about is f of x equals x squared. What is the inverse function of that? Well, if you think about this, if we look at just purely from the graphing sense, if we were to reflect that across the line y equals x, it would look something like this. Oh, let me use a different color. It would look something like this. Ah! Now that's a problem, because we can tell right away with the vertical line test that red thing is not a function, is it? Because notice, for example, at the point, x equals 2, we have 2 different y values. At x equals 4, we have 2 and -2, etc. So this is not a function, and we want our inverse function to be functions. So sometimes what we'll do is we'll limit the domain of the original function when we create the inverse function. So in other words, we're going to just look at just the positive part of the original function. So we're looking at just that and reflecting that, which means then we'd only have this part here. Okay? So we would say the inverse function of this is just square root of x, not plus or minus the square root of x. Because square root of x would give me this thing, minus square root of x would give me that bottom part. So we say the inverse function of x squared would be just square root of x. And again, so that it is a function. And when we eliminate this, we're really not eliminating any y values. Notice the domain is limited, but the range is still the same. The range still goes from 0 to positive infinity, just like it did before. So we're not taking out any domain values for the inverse function. All right.